So today we're going to talk a little bit about the basic concepts, and then we'll kind of go over what are the fundamentals, design trade-off and problems with GPU, right? And also the benefit, obviously. There's a lot of benefit there as well, right? So whenever I buy a GPU, right, this is an older card, 2080 Ti, one of the really good graphic cards back in the day. It's still a really good cards right now. I would be happy if I have this and I use it to play some of these games, right? So I can like fight Tyrant in Far Cry, in the more the virtual world. I can kind of like go back and relive my middle school day. This is a long time ago, like in the Final Fantasy VII, but there's a remake version which I haven't bought yet. Or I can basically torture myself with Elden Ring, right? And at the same time, the GPU is also really good for many scientific applications, and that also expand into like AI and machine learning, right? It seems to be many math operation that works really well with the GPU. But how and why, right? So there are kind of like a three fundamental concepts that are behind, if you will, the GPU, right? Some of the, and I said fundamental concept because obviously it's not just these three things that makes the GPU work, but these are some of the things that you kind of have to understand why GPU get what it has right now. All right. So SIMD is kind of simple. We kind of talk about this in a while, right? I don't think I go into the detail, but the idea is I have one instruction that works on multiple data. So take VL out of your processor, but instead of having different instruction in a one big instruction, it's still one instruction, but they are doing the same thing on a bunch of data, right? Then before we begin, let's kind of dig deeper into the concept of parallelisms, right? So when you look at how fast my program can be, one of the good measures, I look at the wall clock and see how long does it take for my program to run. There's another way to think about how fast is my hardware, right? This metric is called instruction throughput. And the key idea is I look at the number of instructions I finish given the same amount of time. So let's say within 1 hour, how many instructions can I finish on my processor, right? There's also the unit of parallelism, which means you can do multiple things at once. This is kind of like a simultaneous execution of computation. Right? It doesn't have to be a related job. It can be just two programs running at the same time. It can be also related. Things like parallel for loop. So if you look at OpenMP annotation, you can write a for loop this way, and you will notice that B of I equals A of I plus 1 has nothing to do with each iteration. Basically, the current iteration has nothing to do with previous iteration. I can run all of these iterations in parallel, right? There's no dependency. This is a really extremely important thing about GPU performance. You need this property, right? And then you also have fine-grained multithreading, which I do a quick recap on, right? So in the traditional multithreading, you have each thread assigned to one CPU, right? If there's more threads than the number of CPU, you just take turn, all right? When you're taking turn, you context switch into the CPU and say, hey, I'm running now, right? And the OS and the hardware would create the policy to context switch, right? And this can heavily determine your performance. So hardware multithreading basically also means that one CPU can support multiple threads at the same time. If one of the threads is stalling, I switch and run another thread, right? So the idea is I want to maintain multiple contexts and multiple threads of the execution in the hardware. So the benefit here is, even though I have only one CPU to run thing, right? I only want one CPU. I can switch to another thread whenever I have a long instruction. For example, I'm loading some data right now. I need to go to DRAM. It takes a while. I switch to another thread so that I can just do whatever the other thread has to do before I switch back, right? So this idea is kind of being there for a long time. It's called simultaneous multi-threading. So when the processor is busy waiting for a higher level cache or even the main memory, I would switch to another thread to keep the pipeline full, right? One example is the Intel hyper-threading technology, which basically maintains 2 threads, and you allow concurrent execution to do useful work, right? So here's a visualization of this. Let's say I have one CPU with 2 threads, right? I run thread 1, and it has to stall because it's accessing the memory. When it's stalling, thread 2 kicks in and say, hey, CPU is not doing anything, let me run. Once it has to stall, because the thread 2 also has to go access the data, then now hopefully thread 1 is available, so you run thread 1 again. You see how CPU is always running something, so you can get more throughput this way, right? CPU is also always active in this scenario, or at least more active compared to like only one hardware thread, right? So that's simultaneous multi-threading. Fine-grained multi-threading is basically put this on steroid, if you will. Whenever I have a pipeline stall, I switch to a new thread. Whenever the stalls, I switch to another thread. Every single cycle, in fact, I switch into another thread. The problem with this is, well, downside, I would have to maintain a lot of hardware thread. Each thread would take more time to finish because it's always switching to another thread. And you need extra logic to keep the thread context alive, right? So the hardware need to store all the thread information, including more register file for each thread's context, all right? So you also need enough threads to fill in the pipeline, right? So that's I guess the trade-off, right? The benefit is the processing core is always active doing something. You don't have to stall. You can support a lot of parallel threads, right, at the same time. But at the end of the day, it also means that each thread is going to be slower. And you need more hardware to support this number of threads, right? So that's the second concept is used in the GPU. The third concept is called the predicated execution. This has to do with branching, if else or for loop, right? So you look at codes like this, right? You can do obviously branch prediction. There are also other methods that we talked about already, which is predicated execution. I would convert control dependence to data dependence. Basically, I look at condition of my previous instruction and it only commit the instruction if certain things are true. So if you look back at the code here, right? If A is 0, then I would do something in the if and then keep running. If A is not 0, I also keep running in the else, right? So depending on what has to be done, I would mark off and not do the other side of the loop or branch. All right, so that's the key idea of predicated execution. And GPU use this to get rid of basically branch in the code, right? You can use if else, but GPU would then convert this to something. It still look like if else. It's not fully predicated execution, but they execute both sides and mark off the side that's not true, right? So for SIMD, again, as I said, is let's say you have to do a lot of math operation that are the same thing, vector add, vector multiply. The idea is I would use one fetch, one decode, right? I save a lot of hardware on the fetch and decode unit. I fetch one instruction, but they are operating, they're adding a bunch of data or they're multiplying a bunch of things together, right? So the SIMD model, which is single instruction, multiple data. And SIMT model, which is single instruction, multiple thread. So one instruction would be a collection of different threads that do the same thing. And here's the requirement. The program counter points to the same instruction, which means that they have to do the same thing. All right. And the GPU recap is SIMD, SIMT plus fine-grained multi-threading. That's it. That's how the GPU works. That's the magic. That's the magic. That's the magic behind how the GPU gets so much performance if the condition is right. Again, the condition has to be right, then the GPU will perform really well. All right. So, oh, sorry about animation, but so let me get rid of those. I'm sorry. I should not have drawn this beforehand. So if you look at the GPU core, or sometimes we call this simultaneous multiprocessor, all right? So you have a CUDA program. The CUDA program that you write, or let's say use PyTorch. PyTorch, at the end of the day, is a CUDA program underneath all those libraries, all right? It being broken down further into a bunch of thread blocks. Something we call this a grid. It's a collection of threads. So all these smaller boxes here are one thread. And there's another smaller unit called a warp. It's a collection of threads put together is a warp. Then if you look at a GPU, you're going to have a bunch of SM. These are actual GPU core. These are the actual GPU core. It's called simultaneous multiprocessor. In AMD terms, it's called streaming multiprocessor. All right. These are what run your code. It has a fetch. It has a decode. It has to have a lot of execute units. So it would send this thread block into each of these SM. Then one warp will be forwarded to the execution unit at any given cycle. So you run this in parallel, and each of these thread block will be distributed across the SM. Some of them will go to the same SM, right? So your program will always run in parallel, right? So one quick note here, you see that the core is the SM, right? If you somehow buy a GPU, you might see something called CUDA core, right? It's something I would say is really kind of should not define as a core, to be honest, right? So I would use this word. So it's like a PR misinformation stunt kind of thing. It's not an actual core. The actual GPU core is the simultaneous multiprocessor. That's be what you think of a CPU core. That would be what is the more one-to-one, more apple-to-apple comparison. Don't compare the number of CUDA core with the CPU core. That's not a fair comparison because you are all scientists, you're PhD students, so be aware of this, all right? Look at the number of SM, that's the actual core. Now let's go back to our 5-stage pipeline we have here, all right? And the focus is forget about everything. Fetch, decode, execute, memory, write back. That's what I want you to remember. I do fetch, which I have a bunch of structure added to fetch, decode, execute, memory, and write back, all right? You can then have things like branch predictor logic to accelerate branches. You can have the instruction scheduling logic, reservation station, future file to accelerate the execution of one thread. You would have the SRAM cache to make things faster whenever you have to access data. And you have the architecture register file to support precise exception, right? So that's a CPU. That's what you learned so far. And the goal here is to make sure single thread performance is good. I want to run one thing, and that one thing is going to be extremely fast. Extremely fast. Now, let's look at how GPU design things. All right. So for GPU, the idea is let's take away a bunch of these things to make room for a lot of the area. So add a lot of adder multiply. These are floating point units, and typically basically the unit that would be added to support a lot of graphic application in a traditional sense, and now AI and machine learning, and now scientific application. Then, because I need to support fine-grained multi-threading, your register file will be huge, right? And because they're getting really big, what I need to sacrifice is I would now have a smaller cache. And some of these cache can be software managed, all right? These are added not to make one thing really fast. One thing is going to be really slow, to be honest, but you get so many things to run at the same time. So your instruction throughput goes up to the roof. So if you can do a lot of things in parallel, if your program writes in a way that's super data parallel, it will be extremely fast. If not, it's going to be extremely slow. Because when you run one instruction in the CPU, it's one operation at a time. But in a GPU, you execute one warp. that has many operations. That have many operations. The number of CUDA core, if you will, right? So the benefit here is you get many operations that can be done in one cycle. You get a really high throughput, right? Now, if I have instruction that takes more than one cycle, I can have stalls, right? So over here, it's a more zoomed in version of the GPU core. In the core, as I said earlier, a thread block is scheduled there. A thread block consists of multiple warps. So each box here is a thread, right? And the way the GPU would run is over time, each cycle, it would pick one of these warp and run in lockstep. And then in the next cycle, I switch to the next warp, then to the next warp, then to the next warp. And let's say warp A is a load and store, then we have to go to DRAM. In this case, I would issue, for example, this has 8 threads, right? So I issue 8 parallel data access. Again, this will take a long time because I need to access 8 things in parallel. But at the same time, I still have warp B, C, and D, so I can keep running. GPU is going to become active, basically, running something useful. It will stall only, like only when all these warps are stuck doing long latency operations like load. I have to go to DRAM. It takes a while. All of them are there, so I need to wait until some of these are back. When they're back, then I resume execution again, fast again. All right. So as you can see, there are clear trade-offs. You get so much throughput because you have number of cores plus each core has multiple links. So that's the really high instruction per cycle. But for the single thread performance, it's really bad because you don't have the complex out of order scheduling. There's no branch predictor. There's nothing to assist the execution of one thread. So your program performance depends on whether your application can be done in parallel or not. If you can, it's going to be really, really fast. If you cannot, it's going to be really, really slow. All right. So some of these use cases include things like graphic application, because graphic pipelines have a lot of redundant instruction. I want to draw a dot, triangle, line, then I want to raster the image, smooth out the surface, draw the surface, blah, blah, blah. These are similar instructions that do the same thing over and over and over and over again, right? There's a lot of adding and multiplying, right? So these are some primary use cases. Now, I talk about why GPU can be really awesome, right? When it's really good, it's extremely good. That's why people buy the GPU. But what about the case where it can be slow because of how you program? For example, if you have an if-else like this, right? If A equals 0, do something else, do something else. All right. Now, let's look at this warp. Let's assume this warp has H thread, right? And let's also further assume the first 2 threads is true. The second 2 is false. Then you have true, false, false, false. So some of them has to do the if, some of them has to do the else. What does the GPU do to handle this case? What actually is being done is it will go and run both sides of the branches. The first time it will go in, run the true part. The other false part of the thread is blocked out. I'm not running anything there. It keeps running. And once I'm done with if part, I then execute the else part. So as you can see, right, the performance will drop. We call this problem branch divergence. Because from the earlier example, you do not actually utilize execution units at once, right? So this lower the GPU performance. All right. For example, let's consider this. I have an array A that has some random value, right? I have array A that has random value. Can you answer this question? If I have 64 lanes, okay, actually let me change the number quickly here so that it makes things a little, oh, sorry. Yeah, actually that's okay. So let's say if whatever elements of A is divisible by 3, it would do the if, otherwise do the else. And as you can see here, the if takes 1 line, the else takes 2 lines, right? I can ask you things like, assuming that I have a GPU core that has 64 lanes, so this loop will parallelize into those 64 lanes. They're going to be 1024 divided by 64 warps that you can run, right? These are 1024 threads. There's nothing that there's no dependent instruction across the iteration, so I can fully parallelize them. Then I can ask, what will be my GPU core utilization given certain assumption about the array A? Given certain assumption about the array A. For example, if I say the array A is all 0, if A is all 0, means that it always fall into the if, right? It never do the else. So in this case, GPU is fully utilized. I always have to go to the if. I just ignore the else. There's nothing that I need to do there. I can just skip that. But let's say for the array A, it has non-divisible by 3 mixed in. Now you lose performance because some thread will be run in the if, some thread will be run in the else. Your utilization dropped. For on your sample final exam, there's more questions about this, so you can practice there and you can ask me questions about how to approach these things. So let's do it when you're doing the review session. All right. Now, that's handling branch. To handle data access, right? Similar to the CPU, GPU have everything that looks like the CPU, but more parallel. So you can do load store unit. You can access the cache. You can access the memory. Most GPU doesn't support the same complex virtual memory as we know it from the CPU side of things. It's simpler. It's simpler. GPU driver would handle memory location. Doesn't mean that we have a typical virtual memory benefits. Some GPU back in the day doesn't even have memory protection, so you don't have the illusion of large memory. Now, the newer GPU does have a virtual memory support, so it does have memory protection. It does have a way to map data in between the CPU memory and GPU memory, but still it's an overhead that has to be managed. All right. Now let's look at the cache. Right. So if you look at the CPU, right, CPU, you have two memory access, load A and load B. If it's a cache hit, it's awesome. The green thing is just awesome. It goes to the cache, quickly get the data, come back, resume execution. If it's a cache miss, I go to the memory. It takes longer time. All right. So the stall time of A is that long, while the stall time of B is much quicker. The cache is there to make the memory access a lot faster. All right, it's there to make the memory access a lot faster. Now let's look at the GPU and the problem we call memory divergence. So let's look at this warp A. Let's assume that some of these warp hit in the cache, some other miss in the cache. What you see is when you run warp A, the 3 threads that hit in the cache would quickly get the data. But here's the problem. Warp A cannot go. It still need to get those 5 blocks of data from the memory, right? So the stall time of A in this case is as long as the slowest guy in the warp, right? Its stall time is as slow as the slowest as slowest guy in the warp. Again, because it's the memory divergence problem. So again, GPU is awesome. It can be really, really fast, but it does have its own collection of problems. The branch divergence, the memory divergence, and the fact that you need to program in a data parallel fashion. Some algorithm works really well. Some algorithm does not, right? So you might need to redesign the algorithm. Or another thing is you can make the GPU better from the hardware point of view, right? So there are a few examples of my own research. So I'll talk about this quite, basically I'll transition to some of my research. So before I do that, let me ask you if you have any questions so we can take a quick break. And then after the break, I'll dive deep into some of the things I've done in terms of research on the GPU side. So I guess I'll stop the recording so they can watch the video. If there's any questions, feel free to ask me. All right.